Okay, so this is quiz number 2 stuff 2014 in the fall. I should start doing this 351. All right. Person had a question about hyperconjugation. What was that all about? What was the point of hyperconjugation? Who remembers what that was all about?
Wasn't it about the stabilizing the p orbital with the sigma, like the hydrogen?
So something about stabilizing a p orbital with some other sigma bond, right? And more specifically, we were talking about an empty p orbital. So when do we have empty p orbitals? We have empty p orbitals with carbocations, right? So hyperconjugation has something to do with carbocations stability, actually. As you can imagine, all carbocations are not created equally, right? So we know that carbocations are what hybridization state? We learned this in for the first test. We learned they're sp2, right? Because opposites attract, right? We want to get you think about, right? If we draw something that's sp2 here, right? This orbital right here is empty, right? We want to get this as close as possible to the electrons in these bonds, right? Of course, this bond angle here is what? 90 degrees, right? Which is closer than 109.5, right? Hence sp2 versus sp3 hybridized state. Good. So now that's one interaction that makes it stable. We talked about hyperconjugation as another type of interaction that can stabilize a carbocation. And that's with electrons in bonds 2 bonds away. Right? So let's say we have a methyl here. I'll just say we have a H there and a couple other carbons here. All right, so what can happen is this orbital is empty, and we know this is vertical. We know this bond angle is 90 degrees. What's the hybridization state of this carbon right here? It's sp3. So these bond angles are 109.5, right? So it's not perfectly, these aren't perfectly parallel to each other, right? Does everybody see that? But even though they're not perfectly parallel, the electrons in this bond, right, can help stabilize that empty p orbital. And that's what hyperconjugation is. Now, you got to remember too, though, this bond rotates, right? This bond rotates. So these bonds also help stabilize, right? And now this isn't perfect, right? This bond angle is 109.5. This is, perpendicular. This is 90. So this isn't perfect stabilization, but it's better than nothing, right? And notice how, where are these, what bond is this? This bond is 2 bonds away from the empty p orbital, 2 bonds away. So any sigma bond that's 2 bonds away, right, can stabilize the empty p orbital by hyperconjugation. So in this case, right, there's a sigma bond here, a CH sigma bond. There's a CC sigma bond, and another CC sigma bond. So there's 3 instances of hyperconjugation buddies helping stabilize this empty p orbital. Right? So the more hyperconjugation buddies you can have, the more stabilized you'd be. Right? And that gets us to our terms primary, secondary, and tertiary. We talk about carbocations. So primary carbocation is a carbocation that's bound to one other carbon. And it's a primary carbocation. A secondary carbocation is a carbon that's bonded, has a positive charge, that's bonded to 2 other carbons. And then a tertiary carbocation is a carbocation bonded to 3 other carbons. Now, if you look at these, the hard part is we don't draw on H's in organic chemistry, do we? We don't draw on the CH bonds. But are they there? Right? So if you ever have a doubt, draw the CH's in. Right? This carbon has 3 CH's, right? So how many hyperconjugation buddies does a primary carbocation have? Should have 3, right? 1, 2 bonds away. 3 hyperconjugation buddies. How many does a secondary carbocation have? How many would it have? It should have 6, right? Draw those H's in. Does it matter if they're CH bonds or CC bonds? No, right? Up here, this is a CC sigma bond. It doesn't matter. As long as it's a sigma bond 2 bonds away, a sigma bond 2 bonds away. It doesn't matter. So a secondary has 6. How many do you think a tertiary has? So it has 6. Tertiary will have 9. I'm not going to draw those in. But it doesn't matter what kind it is. It has to be a sigma bond. It doesn't matter if it's a CH or a CC sigma bond. Just a sigma bond 2 bonds away. So sigma bonds 2 bonds from the plus charge, right? Doesn't matter if it's a CH, CC, CI, anything. Could be anything. As long as it's a sigma bond 2 bonds away. Okay. So question about UV Vis Spectroscopy. All right, basically what everybody needs to know for this first quiz, or quiz 2, is what does it tell us and what happens in this experiment. Right. So what does a UV vis tell us? What must be there for there to be a UV vis? There needs to be pi bonds, and I'm just going to say pi bonds. There needs to be pi bonds. Right? So if something's UV active, it has pi bonds. If there's pi bonds, Todd, therefore, UV vis active. Right? Therefore, it's UV vis active. If it has pi bonds, it's UV vis active. So what happens in a UV vis experiment, though? So what happens is, right, you have pi bonds. You have electrons in those pi bonds. And you have pi star, right, the antibonding orbital. Right? So there are some terms, HOMO, highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. All right? So what happens in a UV vis experiment, right? Unlike a mass spec where we break bonds, or we knock an electron all the way out of the molecule and start breaking bonds, make positively charged fragments, and unlike in an IR where we shake, right, we shake up the molecule and vibrate it, in a UV vis, we just excite one electron, right? So what happens? We're going to excite an electron. So it goes from pi to pi star. So it jumps up, gets excited. Right? We hit it with some energy, and it goes to a higher energy level. Right? This axis is E. So it gets excited. So UV vis tells us there's pi bonds. And what happens in the UV vis experiment is an electron in those pi bonds gets excited. It goes from pi to pi star. No bonds break. Bonds don't break. Right? But we go from pi to pi star, and we can see that energy as it comes back down. Right? We see that energy as it comes back down to the p orbital. Another term for these, HOMO and LUMO, are ubiquitous terms, meaning whatever the highest occupied molecular orbital of those electrons, that's called the HOMO, and the LUMO is the lowest unoccupied molecular orbitals. Right? So that's the lowest empty space. We'll get crazy. So let's look at chapter 14, number 10. Right, so this is a tricky one because sapling's really careful about electrons and balancing charges. So what happens first in a mass spec? The first thing that happens is we're going to lose an electron. And if the molecule has lone pairs, which electron should we lose? One of those lone pair electrons, right? So we submit it to the electron beam. Right? The electron beam knocks out, right? Fishhook knocks out one of those electrons. Right? Notice I just drew it a different way. You should be able to go back and forth between these ways, right? 1, 2, 3, 1, 2, 3. So I knocked an electron out. Now I have a positively charged chlorine. What would this fragment show up in mass spec? Yes, it would. Why? Because it has a positive charge is why it would show up. So it has a positive charge. That's why it shows up. What is it called? What is this fragment called? The molecular ion, right? It's the whole molecule minus one electron, right? Electrons have mass, but do they have a lot of mass? No. So now at this point, there's a couple things that can happen. With chlorine, right, we can do heterolytic cleavage and homolytic cleavage. With bromine, we can only do homolytic cleavage. So which one do we want to do first? So they ask for both. The easier one to do, I'm going to draw the molecule twice. All right, the reason I drew the molecule twice is because if I'm going to do two different things to it, it's easier to have two molecules than to try to do two things on one. It just gets less confusing. So both are on the molecular ion. So let's do, on this one, let's do the heterocleavage. So what happens in the heterolytic cleavage? Two electrons move. And where are they going to move? Right? Let's take these two electrons in that bond and move them to the chlorine. And while we're at it, let's number our carbons. One, two, three. So what bond did I break here? 3 in Cl, right? Good. Where should the plus charge now be? On the carbon. Good. Do we see that? Does everybody see that? Right, the chlorine doesn't have a charge because now the chlorine has 7 electrons around it. How many electrons does chlorine normally have around it? 7. So chlorine's fine. Right? That's taking 2 electrons going with the chlorine. So the plus charge is now on 3. So what fragment would we see in the mass spec then? The 3 carbon piece, which we should start recognizing as mass of 43 by now. Right? 43. So now the other way we can do this is the homolytic cleavage or the alpha cleavage, where we break an alpha beta bond from the radical. Right? So carbon 3 here is the alpha carbon. That's the one that's bonded to the radical. That's the alpha carbon. Carbon 2 is the beta carbon. Right? So we're going to break this bond right here. So to do that, we're going to have to move those electrons, right? So one electron is going to go between carbon 3 and Cl. The one lone electron from the chlorine is also going to go between 3 and Cl. The one electron left between 2 and 3 is just going to carbon 2. So what bond did we break here? So before we broke the carbon 3 to chlorine bond, what bond did we break in the alpha cleavage? Between 2 and 3. Good.
How do you know which one's the alpha beta bond, or why do you pick between 2 and 3? Choose those electrons?
I pick those because the carbon that's bonded to the thing that lost the electron is the alpha carbon. This just is the alpha carbon. And whatever's bonded alpha, next to it is the beta position. And I picked that one because that's the most likely one to break versus a CH bond. Usually CC bonds break first. And this is particularly difficult because we don't give you the mass of the product, right? If I told you the mass of the resulting fragment, that'd be easier to pick out which bond needs to be broken, right? Okay, good. So, what new bond did I make? I made a what kind of bond?
Pi bond.
I made a pi bond. Right? And carbon 3 still has the H's on it, right? That always had on it. And where is the radical? Where should the dot be? On carbon 2. Good. What am I missing? Balance my charge. Where should the plus charge be? On the Cl. Good. Alright, so which fragment would I see? If I box them in, I'd see this fragment, and I would see this fragment. So this is fragment A and B, and I'll call the molecular ion C. Which one are you more likely to see? Which one would you guess is going to be the base peak? A, B, or C? So that'd be fragment A. Why fragment A? So A is stabilized by hyperconjugation, that's correct, right?
Charges on carbon and
Who would you rather have the plus charge? An electronegative chlorine or a carbon? Right? So yes, this I would guess is the base peak because it forms the most stable fragment. These other fragments form, to be sure, right? But I would guess the plus charge on the chlorine is not going to be the most stable fragment. You're not going to have a lot of those. Take it even another step further. What's going to be different? So, what is this way? Carbon. Let's analyze fragment B a little more. So let's look at fragment B. What's the mass of fragment B? What should the mass be, that peak that we expect? So 12 plus 2 is 14, plus 35 is 49. So it should be 49 when it's chlorine 35. What about when it's chlorine 37? What's the mass going to be? 51. So you should see a peak at 49 and also a peak at 51. And the peak at 49 should look, say, like that. And the peak at 51 should look what height? About a third of that. Yeah. If that's 49 and that's 51, right? These isotopes exist in a 75-25% ratio. So you'll see that in the mass spec. Any fragment that has a chlorine, right, you should have a 3-to-1 ratio of those peaks.
So like if you told us to do like the alpha cleavage for like something like chlorine or bromine, do you want us to show, like, let's say we have to write down the MZ, whatever thing?
Yep.
Do you want us to do it for both isotopes or just one?
Depends how I phrase the question, right? I want you to recognize, you should certainly recognize that chlorine and bromine have isotopes, right? Bromine's 79 and 81, chlorine's 35 and 37. Chlorine's a 3-to-1 ratio, bromine's a 50-50 ratio. So you definitely should be able to recognize that, for sure. All right, I guess I may have misspoke. So for a bromine versus a chlorine in these mass spectrums, because the carbon-bromine bond is so much weaker than a carbon-chlorine bond, if you submit both of these to the electron beam, right, in a mass spec experiment, chlorine, because it's similar in size to carbon, can do both hetero and homolytic cleavages, right, like the alpha. But because bromine's so big and its bonded carbon is not very strong at all, it'll never do the alpha cleavage, right? Because remember in the alpha cleavage, you keep this carbon-chlorine bond, right? So carbon-chlorine bond's stronger than a carbon-bromine bond. So the carbon-bromine bond is always going to do heterolytic cleavage. It'll never do, oops, it will never do alpha cleavages.
And that's because of its size.
That's because bromine's bigger, right? And so the carbon-bromine bond is weaker, and it's just easier to break it heterolytically.
So like on the quiz, would you give us like how you would phrase the question would be like you gave us a mass and then from those two masses we would work backwards kind of figure out.
Yeah, so you should be able to do it both ways, right? You should be able to look at, and that's kind of homework did too, right? You should be able to do it both ways, where you're giving a mass and a starting material and say what is a likely peak this came from, right? Or you should be given a molecule and say give me some likely fragments,
Okay.
right? Let's do another cleavage, but let's do it with a unsymmetrical ether. So with an unsymmetrical ether. So draw in the lone pairs and the oxygen. So the first step is the electron beam. So what are we going to knock out here? Knock out one electron of where? From where? Does it matter which electron I pick? Nope, doesn't. Okay?
It doesn't matter what electron we pick. Why do we always take an electron from like oddball?
You always take it from a lone pair, but my point there was it doesn't matter if you take it from this electron, that one,
okay.
that one, or that one. Right? You always take it from a lone pair.
Okay.
Right. You can imagine which lone pair would be. Ooh. What if you had multiple molecules or a molecule with multiple elements with lone pairs? Then how would you pick? What would you have to think about to pick which electron would be the easiest to knock out? Nice. So like the least electronegative atom would be the easiest one to lose a lone pair, right? Or lose an electron even. Good. Okay, so let's get back to this. So we can do heterolytic cleavages on either side of this, right? Let's number our carbons. 1, 2, 3, 4. All right, we can do heterolytic cleavages both ways, right? Everybody see that? The heterolytic cleavages? So we'd have a 3-carbon piece that could weigh 43, or we could have a 1-carbon piece that would weigh 15. All right, see the heterolytic cleavages? Because, right, I'll just draw those without the arrows, but you should be able to see these. That could be one way, and then it'd be CH3 with a plus. And that'd be carbon 4, 1, 2, 3. These are the heterolytic cleavages. They're certainly possible. But the alpha cleavages are possible as well. All right, so let's look at a couple possibilities for the alpha cleavages. You want to go right or left, guys? Let's go right. Good call. All right, so we're looking for alpha carbons, and whatever that's bonded to is beta to it, right? We want to break that alpha-beta bond. Well, here's the alpha carbon. What's it bonded to beta? Only hydrogen, right? So we got to draw those hydrogens in. So I didn't say it was impossible to break a carbon alpha beta hydrogen bond, right? It's just less likely. All right, so here we're going if this carbon's alpha, this hydrogen, actually all these hydrogens are beta. Right? They're all beta. So we're going to break this alpha beta bond. So we draw on those electrons. Right, we draw on those electrons. Electron from here goes there. The electron goes there, right? One thing you always remember, right? What's the result of an alpha cleavage? You always form a pi bond, right? Between the thing that originally lost the electron and whatever it's bonded to. Right? So make sure you always do that before you even start drawing your arrows. Sometimes it's helpful. Where's this other lone electron going to have to go to? This one's going to go to the carbon? This lone electron. Where's this lone electron going to go? It's going to go to the hydrogen. Right? You're breaking the alpha-beta bond. This carbon's alpha, this hydrogen's beta. One electron from this CH bond is going to help form that pi bond between O and 4. So the other electron has to go to the H. So over here, nothing changed. We formed a pi bond. Right, we formed a pi bond right here with these two electrons, form this new pi bond. Right, so we form that new pi bond between O and carbon 4. And there's still, these other two H's are left. 1, 2, 3, 4. And we also formed an H dot with one electron. And now I need to balance my charge. Where should the plus charge be? On the oxygen, right? Good. Right, so if the pi bond always forms between the thing that has the dot or the plus charge and the alpha carbon, whatever's beta always gets the radical, gets the dot. The beta thing gets the dot. So if this is an alpha cleavage with this unsymmetrical ether, I could also do the same thing with this alpha carbon, right? Carbon 4 is an alpha carbon, but so is carbon 2. It's also an alpha carbon. Right? So if I kind of redraw this over here, this molecular ion again, right? Carbon 2 is also an alpha carbon, and carbon 3 and 1 are also beta carbons. But now you can even imagine, I could make this even more complicated. Because what if carbon, you kind of see carbon 1 and carbon 2 are kind of exactly the same? Right? There's no real difference between them. But I could make them different, right? And then we'd have even another way to break these bonds. But I'm not going to do that to you just yet. Okay? Right? So these two are the same, so it doesn't matter which way I go. Carbon 2 is an alpha carbon. 1 and 3 are the same type of beta carbon. Draw it again. Draw those electrons in there. We know we want to form the pi bond between carbon 2 and the oxygen. And whatever's beta is getting that radical, that one electron. So we'd have the plus charge on the oxygen. And we'd have a CH3 with a dot. And the CH3 with a dot is what number carbon? It's carbon number 1. Because this is 2, 3, and 4. So we broke the bond between 1 and 2. So both of these alpha cleavages are equally, or they're both likely. I don't know if they're equally likely or not. We'd have to look at the mass spec. But with unsymmetrical things, this can happen too. So it can get pretty complicated with ethers, right? Because you can go either side versus the chlorine. Chlorine, you can only go right to one side. So let's look at resonance, right? So delocalization of electrons and how that can affect wave numbers. So electron delocalization. So the example we talked about a couple times in class was an amide, right? So a carbonyl, C double bond O, bonded to a nitrogen. We're talking about IR here. We're going to talk about IR. So we're talking about IR and the C double bond O stretch. Squiggly line. Squiggly line. And how things that are bonded to this C double bond O, how they can affect that stretch. How things bonded to the C double bond O affect that stretch. With an amide, the most important factor is resonance, right? Which means this nitrogen delocalizing its lone pair towards this carbon-oxygen pi bond. So that means this molecule exists like this as well. It exists like this as well. So what that means is, right, this C double bond O sometimes is more like a CO single bond. Right? So how is that going to affect the frequency of the wave number? Right? So if you have a short bond, right, we know an alkene, a pi bond, a double bond is a shorter bond. Shorter bonds stretch at a shorter frequency, right? It's like a tighter spring, right? It's a shorter frequency. That gives you a higher wave number, right? But if you exist sometimes as a single bond, right, your spring just loosened up a little bit, right? So in this case, resonance will lower the wave number, right? Because it's going to have a lower frequency. It's going to stretch at a lower frequency. So this is a case where resonance lowers it. The problem is, resonance doesn't always lower it. It does in this case. Okay, so resonance will lower the wave number in this case. What's a case where resonance will increase the wave number? Is that possible? Absolutely, that's possible. So in that case, we need resonance to take a single bond and make it more of a double bond. Now, how is that possible? Well, let's take a look at this guy. What about this oxygen next to this aromatic ring? What's a resonance structure for it? Right? Basically, that means how can we move the lone pairs towards a pi bond? Right? So if I move these two electrons here, and I take these two electrons and put them on that carbon, I've made a resonance structure. I've made a negative charge here. Now there's a plus charge on the oxygen. So in this case, what I took, what normally was a CO single bond, sometimes with its resonance structures, this CO single bond is now a CO double bond. So if it was single and now it has some double bond character, what's that going to do to its wave number, its frequency? It's going to, if it has some double bond character, now it's going to be like a tighter spring versus a regular old normal CO stretch. So in this case, resonance is going to will increase the wave number, right? Versus a normal CO single bond stretch, right? So now we got done talking about resonance and how it can both lower the wave number and raise the wave number, depending on where if it's giving more single bond character, double bond character. Let's talk about a situation. Well, how do we know if resonance is important? Right? How do I know resonance is important versus, say, induction? So the classic example is our amide versus our ester. Right? We're still talking about the C double bond O in both cases and how the piece attached to it affects that stretch, right? How it affects that frequency. So we know with an amide, resonance is the most important factor, right? We just got done talking about that. The nitrogen delocalizing those lone pairs and donating them. Right, so nitrogen is more likely to donate its lone pairs. Now what about oxygen though? So what do we know the difference between oxygen and nitrogen is? Electronegativity, right? And which one's more electronegative? Oxygen or nitrogen? Oxygen is, right? So who's less likely to donate its lone pairs? Oxygen or nitrogen? Oxygen. So oxygen's not going to do it. It's not going to donate its lone pairs. Well, no, that's not true. It will. But the most important factor is not that. In this case, the most important factor is induction, right? Where the oxygen is simply pulling away electron density, right? And what that's going to do to the frequency, right, it's going to make this CO that much more tighter, right? Because we're pulling away electrons. It's going to shorten that bond up, right? It's going to increase the frequency at which it stretches. And if it increases the frequency at which it stretches, what's that going to do to the wave numbers? Increase, right? The frequency and the wave numbers are directly correlated, right? So this will have an increase. Oh, good God. Increase. Oh, no. Increase the frequency. Therefore, increase the wave numbers, right? Make that bond that much shorter, right? Tighten that bond up. So that's the most important thing with an ester, right? CO. So that's what it's going to do there. Versus resonance, right, which we of course know gives some single bond character. Now I'm going to guess induction. Well, you should guess. Is induction always going to increase the frequency and increase the wave number? No, probably not always, right? Because saying something's always something is never right. All right, let's think of a creative way to apply, let's do an acid fluoride, we call these, and an acid iodide. Both these compounds don't exist in reality because they're both reactive for probably different reasons, right? But what's different between fluorine and iodine, right? So whenever you get problems like this, what I would do is say, well, what's different? And then look at the periodic table and say, how do they relate to each other in the periodic table? So in this case, we have a fluorine, we have an iodine, right? And let's say I'm asking, how does the CO stretch change? Right? What's the difference between these things? How does it change? Now, I honestly have no idea what the answer is here. But we could give rational reasons, right, that would be totally acceptable and you'd get points for, right? So what is the difference between fluorine and iodine? Right, so I literally, ready? I'd write, if I were you on your test, on your quiz or test, I'd write iodine is larger. Down periodic table. Boom. I might even do this. I don't know yet. We haven't got that far. I'm just writing down facts right now. And so how's this going to? So iodine is larger. It's good on the periodic table. Fluorine is more electronegative or less electronegative than iodine. Fluorine is more electronegative, right? I think. More electronegative, right? So it's going to hold electrons tighter and pull them more, right? Which one do you think is more likely? Right, so we're thinking about resonance and induction. Which one do you think would be, if anybody's going to be more likely to donate a lone pair, which one would be more likely to donate a lone pair? Right, so I'm not saying it will, but it's more likely to donate a lone pair. Right, so those are facts, right? We draw a picture, we got some facts, and now we say, well, if you had to guess, I'd guess the fluorine's going to, induction is going to be a big part of that, right? And maybe it's going to make the wave number, what's gonna happen to the wave number then if you have induction? It's gonna increase, right? And iodine, you could say maybe it's more likely to donate a lone pair, and you know, resonance is gonna be a bigger factor there, so it's gonna decrease it. Now I could argue the opposite, actually now I'm thinking about it, I could argue the opposite way too. Carbon and fluorine are closer in size, they're more likely to share electrons in a resonance type fashion. So maybe that's more important for fluorine. Maybe resonance does happen in fluorine because carbon and fluorine are similar in size. I don't know. You could write either one. You could argue. The point isn't the answer. The point is how you state your case.